Today I'd like to talk about how Newton's three laws relate to robotics. Unfortunately, most of you probably aren't familiar with FRC or robotics, so here's a quick rundown. Robot picks up boulder, robot goes over the fence, robot shoots boulder, robot climbs tower at the end. There you go, now you're an expert. According to Newton's first law, it states that a ball at rest will remain at rest, and a ball in motion will remain in motion until acted on by an opposite or unequal force.
A ball can often be a projectile when it is shot into the air into the top goal of the tower.
Newton's second law states that force equals mass times acceleration. In robotics, a small robot can accelerate faster than a robot with high mass if they have the same force.
Newton's third law states that for every action there is an opposite or equal reaction. As you can see in this free body diagram, the robot pulls down on the bar as the bar pushes up on the robot. This is known as an action-reaction pair.
This is a great time to go through a sample calculation of the potential energy that the robot has when it's hanging from the tower. We know that potential energy equals mass times the acceleration of gravity times height. And we have our mass, which is 50 kilograms. The acceleration of gravity is 9.8 meters per second squared, and height is 0.45 meters. So we have 50 times 9.8 times 0.45 equals 220.5 joules.
The equation for potential energy is height times mass times the acceleration of gravity. When a robot is hanging from the bar, it has a lot of potential energy because it has a high mass and is high off the ground. If a robot were to fall, the potential energy would be converted into kinetic energy, and no energy would be lost. Although the kinetic energy doesn't equal the potential energy, this is because some energy is converted to thermal energy due to friction. This is the law of conservation of energy.
At the end of the match, a robot can pull itself up onto a bar to get more points. All the robot has to do is work. Work equals force times distance. The more distance times the more force equals the more work the robot has to do.
A robot with high mass with large motors have more momentum than a light robot with small motors. We know this because momentum equals mass times velocity. With more mass and more velocity, we have a higher momentum. There is a defensive aspect of robotics. Most of the time it is better for a robot with greater weight to play defense because it has a greater inertia.
All robots have kinetic energy. Kinetic energy is energy associated with movement. We know this because in the equation kinetic energy equals 1/2 m times v squared, the v stands for velocity, which is a vector and has motion.